Welcome to CHEM111. We're still in Chapter 4, so this is going to be a Part 2. And in this Part 2, we're going to be looking at dealing with molarity. This is molarity. And molarity is moles of solute in 1 liter of solution. And a lot of times you'll see me doing moles of whatever that solute is, the compound that's provided in the question, equals 1,000 milliliters. And that's because 1,000 milliliters equals 1 liter. And it just saves me a step because most of the time when you're working in the laboratory, you're measuring out solutions in milliliters. So it's molarity is the unit. So you can just write M, big M, for working with solutions. So we're talking about concentrations. And in this chapter, we've been talking about aqueous solutions. So this is in water solutions. Now, the other thing we'll be talking about is dilution. So the other topic will be dilution, and this is a formula you need to know. M1V1 equals M2V2. And I will tell you when to use this. My key thing when to use this is when I see the same concentration, the same solution. So if you are provided with a given amount or concentration of a solution, let's say sulfuric acid, and then you wanted to make a different solution of sulfuric acid. And so when you look for this in the type of questions, you see that you're given one concentration of the solution and then it asks for another concentration of the solution or a volume. But you see you're only given the one solution. And that always triggers this formula that I have memorized, M1V1 equals M2V2, where 1 is the initial, so that's the beginning of where you start, and 2 is your final concentrations. And you will be doing these in the lab. So a lot of you have to do these concentration calculations in your lab practical coming up. All right, so we are going to go straight to your checkpoint problems here. So I'm going to work the following checkpoint problem 451. So problem 4.5.1. Calculate the molar concentration of a solution prepared by dissolving 58.5 grams of sodium hydroxide in enough water to yield 1.25 liter of solution. Now, we want molar concentration, so we want the big M, and we know that the big M is molarity, and we need moles, of this case, sodium hydroxide, in the liter of solution. So what you do when you're given a volume like this is you're going to divide by 1.25 liter, and you're looking for the moles of the sodium hydroxide. So do you know how to go from grams of sodium hydroxide to moles of sodium hydroxide? Yes, you do molar mass. And so molar mass of sodium hydroxide, you look at your periodic table. I'm getting one out right now. Sodium is 23, oxygen is 16, and hydrogen is 1. So that works out to be 23 plus 16 plus 1. That's 40 grams per mole. And then so we can convert 58.5 grams of sodium hydroxide, and for 40 grams of sodium hydroxide in 1 mole of sodium hydroxide. And we knew to put that on the bottom because we need these units to cancel out. All right, so now I'm going to do 58.5 divided by 40. And I get 1.46, I only need 3 significant figures, mole of sodium hydroxide. So now I can put this up here, 1.46, and I'm going to take 1.46 divided by 1.25, and I get my answer to be 1.168 big M. And I only need 3 significant figures because that's all it's given, so 1.17 M. And if you look for that answer, you see that there is an answer, and that is D. All right, so let's go to the next question. The next question, 4.5.2, what is the mass of glucose? Glucose is C6H12O6 in grams that must be used in order to prepare 500 milliliter solution. This is what you had to do in lab. That is 2.50 molar in glucose. Now, whenever I see this here, I make that a conversion factor. So let's make that a conversion factor. And it's 2.50 mole of glucose equal, and we're doing milliliters here, so I'm going to go with 1,000 milliliter of solution. And I just abbreviate that as SOLN. All right, so now I am going to start with my given. And now my given is what a number with a unit. So if this is a conversion factor, we don't start here. We start with the number in the unit. So we put that over 1, 500 milliliter over 1. I do my little train tracks. And this is milliliter of solution. So I want milliliter of solution here, because I got to copy those letters down. And so now I have this conversion factor where I have 1,000 milliliters of solution, I have 2.50 mole of glucose, but the question is asking for grams. So do you know how to go from mole of glucose to gram of glucose? Okay, so that's molar mass, right? So always 1 with the number mole. And then where do we get the molar mass of glucose? Well, we have the formula, C6H12O6. So if I look at the periodic table, 6 times 12.01 plus 12 times 1.008 plus 6 times 16. And so when I do that, 6 times 12, that's 72.06. I have 6 times 16, 96. And then I have 12 times 1.008. And so I get 180.156. And now I do 500 times 2.5 divided by 1,000 times 180.156, and my answer is 225.195 grams of glucose. I see they only need 3 significant figures, so I'm going to do 225 grams. I'm going to look to see if that's an option, and I see that that's an option A. I'm not checking these, so you can check them in the back of the book to make sure that the math is correct. All right, so let's look at 4.5.3. What volume in milliliters of a 1.20 molar HCl solution must be diluted. So here's the keyword diluted. And so when you see that, you should be thinking, okay, I need M1 V1 equals M2 V2. Let's go on. Diluted in order to prepare, so this is the 2 situation, this is your final, a 1.0 liter, 0.0 liter solution of 0.0150 molar HCl. Do you see how you saw HCl twice? So you see HCl here and HCl there. So if you didn't have the keyword diluted, that is another way to know you're going to have to use this formula. Now, the most important thing here is you can define the 1 and the 2. So initially, M1 is 1.20 molar HCl. M2 is what you want to end up with, and it's always going to be less because you can't go the other way. When you can dilute something, you can add water to something and make it less moles. The reason why this works is because of conservation of mass. So if you take the number of moles, so let's say that is your HCl, and you put it in a bigger container, you still have the same number of moles. Okay, so anyway, so here's the M1, M2, and then do we have V1? Now they're asking how many milliliters do we need to add to prepare a final V2 1.00 liter. So now you have to solve for V1. So M1 V1 equals M2 V2. And how do you isolate your variable? It's connected by multiplication, so we're going to divide both sides by M1, M1, and so that cancels that out. Now we have V1 equals M2 over M1, and I just like to keep it together, V2. And so then V1 equals, this is called plug and chug, folks. And once we have a formula, you just have to pull the right formula. Isolate your variable. So M2 is first, so M2 is on top, 0.0150 molarity. M1 is 1.20 molarity, and then your V2 is 1.00 liters. The molarities will cancel out. You'll be left with liters. Keep in mind it wants milliliters, so we're going to have to convert 0.015 divided by 1.200 times 1. So I get V1 equals 0.0125 liters, but I have to say 1 liter, there's 1,000 milliliters, so I'm going to multiply by 1,000, and it looks like I need 12.5 milliliters. 12.5 milliliters, and I look to see if we have 12.5, and I see that there is an answer B. All right, let's go to the next one. Okay, the next one we have a solution 4.5.4 that's 0.18 molar in sodium carbonate. Is also blank, and choose all that applies. So now we want to break this down into its ions. So here we have 2 sodium positives plus 1 carbonate minus. And so I'm going to figure out what's the concentration here of sodium. Now, so 0.18 molar of sodium carbonate, and for 1 molar, well, you know what I like to do. I like just to go straight to moles. So let's just, for fun, make this moles. Okay, and we can do it for this type of problem. Okay, so 0.18 moles of sodium carbonate, because it's the same volume. And then for 1 mole of sodium carbonate, we have 2 moles of sodium. So you can multiply that by 2.18 times 2, and that's going to be 0.36 molar sodium ions concentration, and then 0.18 mole of sodium carbonate. And for 1 mole of sodium carbonate, you have 1 mole of carbonate. And so that would be 0.18 molarity of the carbonate. And I see A is there, and then E. And this one I will check. So A and E. So bear with me. I'm going to look these up. 4.5.4. And I see A and E. Okay. So since it's just asking concentration, and the moles, the theory is the moles stay the same. And that's what you're looking at 4.5 and 4.56. So I will let you work those. Moving on to acid-base titration questions. So I need you to be able to write an acid-base titration reaction and then do some stoichiometry with concentrations for that. Now we're doing acid-base titrations. And when you do a titration, you're adding either the acid or the base, and it's usually with a standard solution. And so that standard solution is a known concentration of either acid or base. And then you do the reaction, and what you're looking for is you usually have an indicator in there. An indicator will change colors when it reaches the equivalence point. So you need to know a little bit of the terminology here. And so the equivalence point of a reaction is indicated by the endpoint. It's also called the endpoint. And that's where the indicator will have a sharp color change. So you'll see that color change. And it's when the moles of acid, so proton, equal the moles of base. And you'll see you get a color change. So definitely read that. Like here in your problem, you get 2 sodium hydroxide, which you know that's a strong base, reacts with sulfuric acid, which is a strong acid. Now what happens here is, you see it's a 2 to 1, a 2 to 1 ratio, molar ratio. Takes 2 sodium hydroxide equivalents to neutralize a diprotic. This is a diprotic base. Now, some people will try to use the dilution equation, M1V1 equals M2V2, rather than to write out the equation, and it doesn't work for the diprotic ones. So do not do that. Not good. You want to always, when you're doing acid-base titration questions, always write a balanced reaction so you can get the coefficients. You're going to need them. Okay. And you will have to come up with writing that equation. So let's work 4.61. What mass of silver chloride will be recovered? Okay, so what mass, gram, of silver chloride will be recovered if a solution containing 5.00 grams of sodium chloride is treated with enough silver nitrate, okay, that means that's your excess reagent, to precipitate the chloride ion? all the chloride ion. Okay, so you want to write your reaction, and this was a reaction very similar to your exam. So you have sodium chloride, and this is aqueous, plus silver nitrate, aqueous. Those are soluble, folks. Sodium is always soluble. You need to know your solubility rules. Chloride is always soluble unless it's with 3 of them, okay, and silver is one of those. Silver is a +1 always, and nitrate is always going to be soluble. So you break those up into your ions, and then you do-si-do. Now sodium's with chloride, now it's going to be with nitrate, and so that's going to be sodium nitrate, and that sodium nitrate, sodium and nitrate are always aqueous, always soluble, and then the silver partners with the chloride, and that is insoluble, so that's going to precipitate. So what you want to do is write this solution here and make sure that it's balanced. So because whenever you're doing stoichiometry, you need a balanced equation, and it is balanced. Okay, so it's balanced. So I always write the equation, the reaction. Now it says 5 grams of sodium chloride is treated with excess silver nitrate to precipitate all the chloride ions. So the question is, how many grams of silver chloride, what mass will be recovered? So what's the mass? So you start with your given, which is the number with the unit, 5.00 grams of sodium chloride, and then you got to convert that to moles. So you got to go to moles of sodium chloride, and then you can go to moles of silver chloride, and then you can go to grams of silver chloride. So Cl is 35.45 plus 23 for sodium. I get 58.45 grams of sodium chloride and 1 mole of sodium chloride. And then I can go from 1 mole of sodium chloride to 1 mole of silver chloride. And it asks for what mass. So for 1 mole of silver chloride, I get how many grams of silver chloride? Well, what's silver? Ag, 107.88. 107.88 plus chloride is 35.45. So that's 143.33 grams of silver chloride. Now I can do 5 divided by 58.45 times 143.33, and that's 12.26 grams of silver chloride. And I see the answer, you can check it, A, is 12.3 grams of silver chloride, which we have 3 sig figs in our given. We need 3 sig figs, so that is correct. All right, so that would be a precipitation reaction. Let's go on and do problems 4.64 and 4.65 to show you how to do a neutralization reaction, which and then a dilution problem. All right, so here we have, what is the volume of 0.144 molar solution of sulfuric acid is required? Let's try to write that properly. So we want to know how many milliliters is required to neutralize 25.0 milliliter of a 0.0415 molar solution of barium hydroxide. Now, whenever you see this combination, that tells you moles of solute. So in this case, it's moles of barium hydroxide. And then you can go from moles of barium hydroxide to moles of sulfuric acid. But you need the balanced coefficients. So you need the coefficients from a balanced reaction. So once again, you need to first write the balanced reaction. Sulfuric acid plus barium hydroxide and these break down into ions, 2H plus, SO4 2 minus, barium 2 plus, 2 OH minuses, and then the H plus and the OH come together to make water. You can do aqueous, liquid, and then the barium sulfate come together, and that is a solid precipitate, right? Okay, now we have moles of, is this balanced? It's not. So what do we need to do? Do we need to put a 2 there? And that's 4 hydrogens and 2 oxygens? Yeah, so I think that balances it. All right, so now let's go from 25.0 milliliters of barium hydroxide, and then this is a conversion factor, so that is 0.0415 mole of barium hydroxide equals 1,000 milliliters. So 1,000 milliliters, 0.0415 mole of barium hydroxide, and then we can go from mole of barium hydroxide, so we're here, to mole of sulfuric acid. And what are those coefficients? 1 and 1. Okay. Sometimes they work out that way. And then this is a conversion factor. Anytime you see the big M, go put it in the conversion. Mole of sulfuric acid equals 1,000 milliliters, because we're dealing with milliliters. So then you can say 0.144 mole of sulfuric acid in 1,000 milliliters. All right, and I'm just checking the answer to make sure they're given in milliliters. Okay, sometimes it's liters. So now I go 25 times 0.0415 divided by 1,000 times 1,000 divided by 0.144. And I get 7.20486 milliliters. And I see that I have 3 significant figures. So I'm going to go with 7.20 milliliters and see if I can find that answer. And I do see that answer is A. Okay. The other thing I wanted to do was work a dilution problem. So before we wrap up part 2, let's work a dilution problem. And let's see. All right, I found a problem. Okay, so a dilution problem we could work. How about 4.67? Describe how to prepare 1.00 liter of a 0.646 molar solution of HCl, starting with a 2.00 molar solution of HCl. So you see you have the same substance, HCl. And so when you do this, then you can know it's a dilution, M1V1 equals M2V2, and you define what you have. So if you start with M2, that's a M1, 2.00 molar solution of HCl. And when you could describe how to prepare, so the 1 liter is V2, that's your final volume, and M2 is your final concentration. So what are you solving for? You're going to solve for V1. So you do V1 equals M2 divided by M1 times V2. And so V1 equals, what's M2? M2 is the 0.646 molar solution of HCl, and M1 is the 2.00 molar solution, and then V2 is going to be the 1.00 liter. And so when you do this, the units of molarity cancel out, 0.646 divided by 2, and then you multiply that by 1 liter, and you find that V1 equals 0.323 liters. And so when you describe how to prepare this, and you'll have to be doing this in lab, so you have your solution of 2.00 molar HCl solution. And then what you would do is then you would transfer, so you would pipette 0.323 liters, which is also 323 milliliters, into a volumetric flask. So you'd probably, and you want 1 liter, so you're going to get a 1,000 milliliter volumetric flask, or a 1 liter flask, and you're going to put it in there. Okay, so that's all your HCl, and then you're going to use water and fill it up to the meniscus, because you have a 1 liter volumetric flask. And then you'll invert it and everything, and then that's how you prepare your 0.646 molar solution of HCl.